Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to discuss how to estimate causal effects from data. As an example, we're going to consider the following question. If I decide to put the title of this video in all caps, which means that every letter is a capital letter, is that going to cause the video to get more views than if I didn't put the video in all caps, if I use just proper case where some letters are capital letters and some are not? In order to answer this question, we're going to define the concept of average treatment effect, which quantifies whether on average a certain treatment, in this case to put the title of the video in all caps or not, has an effect on average that is causal. All right, and here the keyword is causal. It's very easy to see if some videos get more views or not. It's much more difficult to determine whether the reason is a certain intervention or a certain treatment, like changing the title. Let's get to it. We're going to talk about the average treatment effect. And here the goal is to estimate a causal effect of a treatment from data. So as I said, we're going to use this running example where we want to determine whether setting titles to all caps actually cause YouTube videos to get more views, or maybe people get annoyed and it causes them to get less views. So here the treatment is to set the title in all caps. In that case, we set the random variable t that represents the treatment to equal 1 or not. And in that case, when it's a normal title, we set the random variable that represents the treatment to be equal 0. We're interested in the number of views of the video, so that's the data that we will have observed, number of views of different videos, which we represent by a random variable y. This is the observed quantity. And in order to determine whether there's a causal effect or not, we're going to use the concept of potential outcomes that we had already discussed in previous videos, but I'm going to remind you what they mean. So here, the potential outcomes are two. One associated to no treatment and one associated to treatment. The potential outcome associated to no treatment essentially tells us what would have happened if we hadn't given the treatment to anyone, if we hadn't set any of the titles to all caps. Of course, that's hypothetical because in the past we will have maybe put some titles in all caps, so we cannot completely observe this, but that's what the potential outcome associated to no treatment represents. Conversely, I don't know why I say words like that I don't know how to pronounce. Conversely, anyways. The potential outcome associated to treatment 1 captures the views if we had set all titles of the videos to all caps. Again, this is just hypothetical because typically we would have set some to proper case, some to all caps, but that's what that potential outcome captures. What do we actually observe? Well, for videos where we did not set the title to all caps, we see the potential outcome associated to no treatment. For videos where we set the title to all caps, we observe the potential outcome associated to treatment, to the t being equal to 1. If we want to quantify the causal effect of changing the title of the video, a very reasonable metric to quantify that effect would be to say, okay, if we had set all the videos to have all caps titles, what would be the average number of views? This is captured by the mean of the potential outcome associated to treatment equal to 1. Let's subtract the average number of views if for all videos we wouldn't have set the title to be all caps, which is the mean of the potential outcome associated to no treatment for all videos. This would be amazing, but of course, unfortunately, the challenge is that we don't get to see the two potential outcomes directly. We just get to see the observed data. Our data look like this. For some videos, we don't apply the treatment. For those videos, the number of views tell us the number of views associated to the potential outcome associated to no treatment, associated to proper case, which means that they're not in all caps. But we don't know what would have happened to that video if we had set the title to all caps. That's a counterfactual. in the language of causal inference. There's another video where we also didn't put the title in all caps. Again, we know what would have happened if we hadn't put the title in all caps, because that's exactly what we did. We don't know if putting the title in all caps would have made a difference. In this video, we did put the title in all caps, which is great because now we know the potential outcome associated to putting the title in all caps, but we don't know what would have happened if we hadn't done that. Okay, and so on and so forth. So now, as I said, these missing variables, which tell us what would have happened if we had done something different to what we actually did, are called counterfactuals because they're counter to reality, to what actually happened. It's completely critical to take them into account if we want to quantify a treatment effect causally. So why do I say that? Because it's actually kind of easy to see what is the difference between the average views for videos where we did set the title to all caps and videos where we did not. That's very easy, right? We take the conditional mean when the treatment is 1 and we subtract the conditional mean when the treatment is 0. Very easy to do. However, the key question is, does that mean that this is because this change in the average of the observed views is because of the treatment? It's because of changing the title of the video. And that's a much, much tougher question. In order to study that question more in detail, we're going to take a little detour and we're going to consider another data set where we have student grades from a school in Portugal. And some of the students take private classes, but we ask ourselves, are these classes actually useful? Here the treatment is whether a student receives private classes or not. So t equals 1, the student receives private classes, t equals 0, they do not. The data that we have is grades from the students, and the observed variable y is that the grade that the student obtained in the course. I think it was a course in Portuguese, or I think it was mathematics. I might be wrong though, but I think it was mathematics. So now our question is, does the treatment, which is taking private classes or not, cause the average grade to increase or not? As I said, it's super easy to go to the data and just check, right? Like check, oh, the average for students that got private classes was 10.94. The average for students that did not get private classes is 9.98. This is out of 20. That's the system they follow in Portugal. So the average treatment effect that we observe, at least with this naive calculation, is almost 1 out of 20. Pretty high. So maybe, the parents that are paying for private classes maybe should be happy. So is this case closed? No, it is not, right? Because it's very possible that the students that are taking private classes are systematically different from the students that are not taking private classes. So in that case, it's possible that there would be a difference in the grade of these groups of students, even if they all took private classes or none of them took private classes. So maybe the private classes are making no difference. How can we determine whether that is the case or not? It is really very tricky. So to see why why the observed average treatment effect might be incorrect, let's take a look at a possible confounding factor. So we also know whether students previously failed the course. Okay, this is in the data set. So for students that previously failed the course, we say that this possible confounder is equal to 1. For students that did not previously fail, we say that this potential confounder is equal to 0. So let's take a look at what the data tell us when we also condition on the confounder. So here, this is the conditional average or conditional mean of the grades when they previously failed and they take private classes. For those students, the average grade is close to 9. If they previously failed and they don't take private classes, the average grade is 6.7. So for those students, it seems that the classes, we don't know if they're helping, but at least the ones with private classes have higher grades. What about the students that did not previously fail? Okay, so these students did not previously fail. The ones that did not previously fail and take private classes, have an average of 11.20. The ones that did not previously fail and do not take private classes have an average of 11.31. So what we observe is that for these students, it essentially makes no difference whether they take private classes or not. If they had not previously failed the course, on average, they have much better grades than if they had previously failed, and the private classes do not seem to make a difference, at least for this group of students. Okay, that's what we see. What is the proportion among the students who received private classes? What's the proportion of students who failed? Around 10%. What about among the people who did not receive private classes? Then it's almost 30%. This is very problematic because this means that among the people that received private classes, there's less students who had previously failed, who are weaker and have lower grades in general. So that's going to inflate the grades of the students that receive private classes just because of that factor, nothing to do with the private classes themselves. Okay. Conversely, for the students that do not receive private classes, those have more students that had previously failed. That's going to bring down the average grade for that group. And it has nothing to do with the causal effect of the private classes. So this shows how the confounder distorts the average treatment effect that we observe. Let's make this very, very concrete by expressing the average treatment effect also in terms of the confounder. So by definition, the conditional mean of the grades given the treatment is equal to this integral. We're assuming here that the grades are continuous, but if they were discrete, we just replace the integral by a sum and the PDF by a PMF. So we're basically looking at all the possible values of the grades and we're weighting by the corresponding conditional density given the value of the treatment. So we can now express that conditional density also in terms of the conditional of the confounding factor by including this random variable C. Of course, we have to sum over all the possible values of the random variable C so that this is equal to the conditional PDF. And now once we include that expression for the conditional PDF, we have that we have a weighted sum weighted by the probability of the confounder given the treatment times this integral, which includes the grades times the conditional PDF of the grades given both the confounder and the treatment. This quantity here is just the conditional mean function given the treatment and the confounder. We have essentially reproved a version of iterated expectation. This just says that if you have the conditional mean with respect to the confounder, then you can take the mean of that to actually get the mean just given the treatment. So if you have the conditional mean given the confounder and the treatment, you can average all of it to just get the conditional mean given the treatment. Okay, why is this useful? Because now we can pull apart these averages that we were observing and see how the confounding factor is distorting them. So in the case of the students that received private classes, we can separate this average in terms of those that had not previously failed and those that previously failed. And what do? We take the corresponding conditional means and we weight them by the corresponding probability that someone previously failed if they belong to the treatment group, or the probability that they did not previously fail if they belong to the treatment group. Okay, so these ones are the ones that did not previously fail. So the probability, these probabilities look like that. And this weighted average gives us the observed average for the students that received private classes. We have separated this into the contribution from the students that had not previously failed and the contribution from the students that had previously failed. We're going to do exactly the same thing for the students that did not receive private classes. Again, we separate the conditional mean function into a conditional mean function where we're also conditioning on the confounder, and now we have to sum all those possible values of the conditional mean function given the confounder and the treatment weighted by the conditional PMF of the confounder given the treatment. When we do that, we again obtain these two terms that when we sum them up, they give us the contribution of the students that did not previously fail and the students that previously failed to the average of the students that did not receive private classes. And here we see very clearly that it's very problematic that this probability and this probability are different, because for those students, the private classes don't seem to make any difference, but those students have much higher grades than the students that previously failed, and there's just more of them. So it turns out that this average here is bigger than this average here because of the fact that the treatment group includes more students that had not previously failed. Okay, and that's kind of ironic because for those students precisely it seems that the private classes actually make no difference, whereas for the other students it looks like the private classes make more difference, but because of this effect where there's just many more students that did not previously fail in the treatment group, this gets weighted down. Okay, so the average treatment effect is completely driven by the fact that there are better students, and by better students I mean students that did not previously fail in the treatment group, not because the private classes are doing anything. This is the same effect that we observed with Simpson's paradox, so you can check out the video on that if you want to refresh your memory. So how can we avoid the effect of confounders? It turns out that we can by randomizing the effect. We already talked about this in a previous video. And the idea is that when we randomize the treatment, in the case of the videos, we would set the title to all caps or not, like independently at random for each video. In that case, the treatment is going to be independent of the potential outcomes. Notice that we're saying that the treatment is going to be independent of the potential outcomes and not, and I have to really emphasize this, it's not going to be independent of y, right, which is the observed outcome, because we know that the y that we observe completely depends on the treatment. Remember that the potential outcomes represent what happens in a hypothetical world where we're like giving everyone the treatment or giving no one the treatment. This captures this independence between the treatment and the potential outcomes, just means that we're not treating people differently based on what their potential outcome would be with and without the treatment. Or perhaps more intuitively, that the treatment group of people that receive the treatment and the control group of people that did not receive the treatment are not systematically different. We're not choosing whether to give the treatment to people based on the quantity that we care about. In the case of the students, we're not choosing to give private classes to students that are better anyways. Okay? Hopefully that makes sense. So if that happens, then it's great, because let's take a look at the conditional mean when the treatment is equal to 1. We know that this is the same as the conditional mean. This is the conditional mean of the grades when the treatment is equal to 1. This is exactly the same as the conditional mean of the potential outcome associated to treatment if the treatment is equal to 1. But now, if these guys are independent, this is just exactly the same as the mean of the potential outcome. Why? Because the conditional mean is equal to this weighted integral or weighted sum if things happen to be discrete, where we have the conditional PDF, but this conditional PDF is just equal to the marginal because of independence. Okay, only if we have independence, and this is critical. If that happens, then the observed average for the people that get the treatment, or in my example, for the videos that I put in all caps, is actually representative of the average of what would happen if all of the videos were in all caps. The intuition is that since I'm not selecting the treatment based on what videos are going to get more views or not, this average is representative. Hopefully that makes sense. The same argument shows that if we have this independence assumption, then the average for the videos that did not get the treatment, that were like the title is not in all caps, is representative. The observed average is representative of the average that we would observe if none of the videos had all caps titles. And in that case, we can just take the observed averages and subtract them to get the average treatment effect. And that's actually what I did. So at the beginning of the semester, I decided to make this into a little experiment. And every time I posted a video on YouTube, I decided whether to put the video in all caps or not, even though I find all caps titles quite annoying, but whatever. I thought this would be an interesting experiment. I decided based on a random coin flip. So I opened my browser and I put random coin flip, and Google does this for you. It gives you heads. In the case of heads, I would put the title in all caps. In the case of tails, I would put it not in all caps. So in my little experiment, 19 videos happen to be in all caps and 26 happen to be in not all caps. And the average treatment effect is essentially 0. So for my videos, which are a very particular type of videos, which are mostly watched by my students and my parents in Spain, who will watch all of them, so that makes no difference, even though they don't understand English very well. For my type of videos, all caps doesn't make a difference. And we can make this conclusion because I randomized the titles. If I hadn't randomized the titles, it could be, imagine that I would have started by putting the titles in all caps, and then after a while I switched to not all caps. Older videos tend to have more views, right? So that would have completely distorted the observed averages. Or maybe older videos were less interesting, and lately I'm talking about more exciting stuff, and maybe the latter videos would get more views. That would also distort. In order to neutralize all possible confounders automatically, we randomized the treatment, and that enables us to make conclusions about causal effects based on the observed data. Just for your information, these are the two box plots of the all caps and the proper case videos, and actually the median, even though the mean for all caps is slightly larger, the median for proper case is slightly larger. This is an outlier. This was the first video that has a lot of views. This tends to happen. So in general, again, our conclusion is that for my type of videos, all caps doesn't make a difference. What if we cannot randomize? In the case of the school in Portugal, it might be very difficult. Of course, you should randomize if you can, because that will allow you to establish a causal effect. But it might be very difficult because parents might complain, like, why isn't my kid in the treatment group? I want him to get, or her to get, private classes. Or you might just have some data and it is what it is. You have the data that you have. For example, in sports, you cannot set up randomization effects to try to establish causal effects from real data from games. So what do we do in that case? Well, in that case, we can try to approximate, to correct for the effect of confounders that we know are distorting the average treatment effect. In order to do that, we notice that the expected value of the potential outcomes, which is what we're interested in, by iterated expectation, is the mean of the conditional mean of those potential outcomes given the confounder. So we can write this, if the confounder is discrete, as a weighted sum of the PMF of the confounder times the conditional mean of the potential outcomes given the confounder. Same thing for here I've only written the potential outcome given treatment. For the potential outcome given no treatment, same thing, except that now the conditional mean would be of the conditional of PO0 given the confounder. So now the question is, do we know the PMF of the confounder? Think of the example with the private classes. We do, right? We know how many people previously failed or not. We can use empirical probabilities to easily estimate that PMF. Do we know the conditional PMF of the potential outcomes given the confounder? That is much trickier. And the answer is that we only know this under a pretty strong assumption. That assumption is that the potential outcomes are conditionally independent of the treatment given the confounding factor. Basically, what we're saying here is that for each possible value of the confounding factor, we have like a mini randomized trial. If that is true, then we have this situation because of independence, the observed average effect is actually the true average effect, and then we can recombine them using the probabilities of the confounder. So let's take a look. What I'm saying is the observed conditional mean given the confounder and the treatment is equal to here we're in the case where we're not giving the treatment. So automatically the observed, in this case, grades of the student is equal to the corresponding potential outcome for no treatment. That is equal to this integral where we're multiplying by the conditional PDF given the confounder and given no treatment. But now, because of conditional independence, this is just equal to the conditional PDF given the confounder, okay? Because T and the potential outcomes are conditional independent given the confounder. Again, this is a strong assumption, but this is the assumption that we need here for things to work out. And in that case, this is actually equal to what we want, which is the conditional mean of the potential outcome given the confounder, which we can then aggregate to get the actual potential outcome. This only holds if we have conditional independence. We can do exactly the same thing when we're conditioning on treatment. Now, if that is true, if we have this conditional independence assumption, we can actually go back to our formula for the mean of the potential outcomes, where we are aggregating the conditional mean of the potential outcomes given the confounder, and replace these averages by the conditional averages observed given the confounder and given the treatment under this conditional independence assumption, which essentially states that for each of the groups according to the confounder, we do have like a randomized trial. In the case of the students, we're assuming that for the students that did not previously failed, among those, the ones that get private classes or not, basically it's independent of whether they're good students or not. Okay, and we'll talk in a moment whether that is a reasonable assumption. But the point is that under that assumption, this is actually equal to the mean of the potential outcome associated to treatment. We do exactly the same thing for the mean of the potential outcome associated to no treatment. And this enables us, under this conditional independence assumption, to estimate the average treatment effect by looking at the conditional means within for each value of the confounder and then aggregating them using the PMF of the confounder. Let's apply this to our private classes example where the confounder is whether the students previously failed or not. And here we have essentially the same conditional means that we had before, but now the key is that we're reweighting them equally, okay, for treatment and no treatment using the PMF of the confounder. So we're breaking this dependence between the confounder and the treatment, and that allows us to not weigh this much higher just because the treatment group have more people that had not previously failed. And this reveals that there is an average treatment effect that is much smaller than the one that we had observed, which, if the conditional independence is true, actually captures the fact that, for this type of students that had previously failed, the private classes seem to be helping. So now, are our assumptions correct? Of course not. I mean, let me give you two examples. Like on the one hand, richer kids tend to get more private classes, and those kids might do better just because they have more resources. Maybe they don't have to work on the side, etc. On the other hand, people that get private classes usually get private classes because they need private classes, so they're weaker. Okay, so that also, would distort the average treatment effect. So no, beyond this confounder that we just identified. The answer is no, our assumptions are not correct. We cannot guarantee that there are no additional confounders. However, is this a better measure of the effect of the private classes than if we had not corrected for previous failures? It is a much better measure. And this is the case often in causal inference. You cannot guarantee from observational data that you're actually characterizing causal effects, but you need to correct for the confounding factors that you actually know in order to get better measures of whatever you're interested in. And then maybe you can follow up with a randomized trial if you find something interesting. But you need the randomized trial to really guarantee that you have a causal effect. And that's all I got. So what have we learned? We have learned that confounding factors can completely distort the average treatment effect. And we have learned that randomization actually neutralizes confounders and enables us to estimate the average treatment effect. We have also shown you how to adjust for known confounders under conditional independence assumptions. And that's all I got. Well, and we have also learned that, at least for my type of videos, all caps titles don't make a difference. Thank you very much.